Alright guys, welcome to our channel. So this time we're going to talk about limits of a function that is under differential calculus. So just a quick discussion. Limits is actually the basic concept of in terms of studying calculus. So therefore, once we already understand its concept, is that it would help us to cope up with the difficulty of studying calculus itself. So this time, let's talk about the theorems or some of the theorems of the limit of a function. So let's put theorems right here. So number one theorem would be look like this. So a limit of a function, or I mean in the number one theorem told us that the limit of some constant c as x approaches to any real number a, that's just equal to the constant itself. So let's put where right here C, I mean let's color that into red. C is a constant, and then A represent, sorry, that has T right here, is any real number. So that will be it. So the limit of some constant c as x approaches to a is just the constant. So let's go to theorem number 2. In theorem number 2, it told us that the limit of the function x as, sorry, let's put x in red color, as x approaches to a, letter a, it's just equal to a. So the limit of x as x approaches to a is equal to a. So basically we just need to substitute the a right here into x so that we will be able to evaluate the limit, and that is equal to a. So a is any real number right here. So let's go to theorem number 3. In theorem number 3, it is talking about a some function that has whole number or constant. Let's say that the limit with a function that has whole number, let's just, or the constant, they are the same. Let's put f of x or some function as x approaches to a. So the only thing that we need to do in this theorem is that, or if we are going to have this kind of limit, is that we need to just factor out the whole number and then evaluate the limit of a function. So that is what we are going to do right now. So therefore this is equal to, let's factor out the constant and then evaluate the limit of a function f of x as x approaches to would be a. So let's go to theorem number 4. And theorem number 4 told us the sum and difference of a function, or the limit of the sum of the difference of a function. So let's say we have the two different function, and it is either separated by plus or minus. Let's say the other function is g of x, and that is x approaches to, that would be a. So how do we evaluate this limit? Is that we need to just evaluate each the limit of each function, and then either add it or minus. So let's evaluate the limit of the first function first. That would be limit of a function f of x as x approaches to a. A represents any real number, and then plus minus would be the limit of the other function g of x as x approaches to would be a. So right now we only have the 4 theorems. Let's go to number 5. number 5. So in number 5, it talks about the product of a two function. How do we evaluate the product of the two function? Let's say that we have a two function that is being multiplied. Let's put that represent multiplication. So we have two function being multiplied as, of course, that is x approaches to a. So just like in theorem number 4, we have to evaluate each of the limit. So but however in number 5 you have to multiply it. So let's evaluate first the limit of the first function f of x. This is f as x approaches to a or any real number, and then multiplied it by the evaluation of the limit of the second function g of x as x approaches to, of course, a or any real number. So in comparison to number 4 and number 5 theorems, the only difference is that in number 5 is in terms of product, and number 4 is in terms of addition and subtraction. So let's go to theorem number 6. Let's put 6 right here. So in theorem number 6 is the division of a function. So how do we evaluate the limit of the two function that is being divided? Let's say that the first function is f of x, that is in division or over the second function, let's say g of x, as of course x approaches to a. So how do we evaluate this? So in terms of evaluating this one, is just like in theorem number 4 and 5, is that we need to evaluate each of the limit of each function. So the limit of a function as x approaches to a divided by the limit of a function of the second function, rather the limit of the second function g of x as x approaches to a, of course. Let's put a. So this would be our 6th theorem. Let's go to number 7. So number 7, this is quite being complicated because this is already in the radical function. So let's say that if we need to evaluate some function f of x, let's put f of x right there. However, there is a radical sign or symbol right here that is some number n as x approaches to a. So how do we evaluate this kind of limit? It's just simple. We need to just evaluate the inside function first, f of x, as of course x approaches to a. We need to evaluate that first, and then once we already evaluate that, is that we need to put the radical sign n right here. So however number that is in this function is just equal to the number of this function once we will evaluate the inside limit, where there is a condition right here. Let's put n is any positive, n is any positive integer, so it could be 2, 3, or 4, as long as it is in a positive integer. And then f of x, sorry, let's color it into blue. F of x is greater than or equal to 0 if n is even. So how do we able to interpret these conditions? So here's what it would look like if these two conditions aren't met. Let's say that if we have a even radical right here, and then if we have a function that is not greater than or equal to 0, that would be negative f of x. So if we try to simplify this one, that would be math error. Basically, there is no real number that we're going to have right here. However, if we have let's say that if we have a add radical right here, if we have a cube root of negative f of x, this one is good. We can evaluate this, that is equal to let's say if we have a cube root of negative 1, that is equal to negative 1. So this is good. However, if these conditions aren't met like this, that is not going to be being simplified. So that would be what would happen if this condition aren't met. So let's go to theorem number 8. So theorem number 8 told us that the limit of some function, let's say some function f of x, and that function is raised to a power, let's say that the power is n is a positive integer. It could be 1, 2, 3. Also in here it could be 1, 2, 3 as long as it is in a positive integer, and x approaches to a or any real number. So how do we evaluate to this kind of limit? So just like in theorem number 7, we need to evaluate the inside function first, or the limit of f of x as x approaches to a. So once we already evaluate this in the inside function, we need to raise all that up by or to n. So whatever values that we have here is equal to what we have here. So alright, so since we already done with all the important theorems for the limits of a function, let's go to examples to understand even more further. So example number 1, so we have here a limit of x cubed plus 7x minus 10 as x approaches to 2. So how do we evaluate this? So since we have 3 terms right here, this is a polynomial that is separated by addition and subtraction. We can use the theorem number 4. So based on this theorem number 4, so therefore, and in each term we are going to evaluate the limit and then add or subtract it. So let's go evaluating this. Number 1, let's put equal sign. Let's evaluate the first term, limit of a function of x cubed as x approaches to 2, and then plus, since we have a whole number right here, we can basically factor that out. So therefore we have 7, and then evaluate the limit of x as x approaches to 2. And then since we have a constant right here, we just have to put limit of 10 as x approaches to 2. So evaluating each of the terms, we are going to have what this. So the limit of x cubed as x approaches to 2, we just need to substitute the x right here. So we are going to have 2 raised to 3 since we have x cubed, and then plus 7 right here. We are going to evaluate the limit of x as x approaches to 2. So we just need to substitute the value of x, that is 2, and then minus what is the limit of 10. So this is in theorem number 1, which is the limit of a constant, where let's go back, the limit of a constant is just equal to the constant. Therefore the limit of 10 is just 10. So evaluating more and or simplifying more, we are going to have the value, which is, this would be 8, this is 14, that is minus 10, so therefore this is equal to 12. So this would be our answer for example number 1. So let's go to example number 2. So based on this function, we have 2 function that here that is being multiplied. So as we going to look back, this is in theorem number 5, which is 2 function that is being multiplied. So therefore we just need to evaluate each of the function differently and then multiplied it. So therefore this is equal to the limit of the first function, x minus 10 as x approaches to 3, multiplied by the limit as right here we need to write the function 3x plus 7 as x approaches to 3. So this one is a under sum and difference theorem, which is in theorem number 4. Let's go back right here, this one. So we just need to evaluate the limit of each term. So therefore this is the limit of x, the limit of x as x approaches to 3 minus the limit of 10 as x approaches to 3, and then we are going to multiply it by this one. So this is in a radical form, therefore this is actually in theorem number 7. As we try to look back right here, this is in theorem number 7. So therefore we are going to evaluate the limit of the inside function first. The inside function of this one is this one, the inside of the radical. So we need to evaluate that. So we have a limit of 3x plus 7 as x approaches to 3, and then let's use bracket right here to avoid confusion. Let's use bracket, and then since we are going to evaluate this, we have to raise this, square this into this one radical, and then that would be multiplied to this limit. So that would be it, and let's put the continuation solution right to here. So let's evaluate this one first. So the limit of x as x approaches 3, so we need just to substitute the value of x, which is 3, and then minus, this is the limit of a constant. The word constant right here is 10, so just need to put 10 right here, as we can see right here, and then that is multiplied to, how do we evaluate this one? So that is radical. So let's just put right there the limit of 3 of x, since we are going to evaluate each of the term as x approaches to 3, plus the limit of 7 as x approaches to 3, and then that would be, so 3 minus 10 is just negative 7 multiplied by the square root of evaluating the limit of 3x as x approaches to 3, that would be 3, and substituting the value 3 since we have 3x, and then plus, since we have a constant 7 right here, so the limit of a constant is just a constant, we just put 7 right here, and then evaluating, we are going to have negative 7 multiplied by the square root of 3 times 3 is 9 plus 7, that is 16. Therefore we are going to have negative 7 multiplied by square root of 16 is 4. Therefore we are going to have negative 28. So this is going to be our answer for example number 2. Let's go to example number 3 directly. So right here we have a sum function that is raised to squared. This is basically in theorem number 8. As we recall, this is this one. So how do we evaluate these limits? Is that we need to just like in number 2, we're going to find the limits of the inside function. So limit of 5x plus 7 as x approaches to 5, and then we're going to raise all that up to squared. So evaluating the limit of the inside function, that is the limit of 5x, since we need to evaluate the limit of each term as x approaches to 5, plus the limit of 7 as x approaches to 5, and then we need to raise all that up to the power of 2. So what is the limit of 5x as x approaches to 5? So we just need to substitute the value of x, so that is 5 times 5 plus the limit of 7. Since 7 is just a constant, we just put 7 right here, and then we have to raise all that 2 squared. So therefore we are going to have, that is 1024. So that would be our answer for example number 3. So right now guys, I'm going to show you the alternate solution for this one, and that solution is basically the simplest and the easiest way to solve or to evaluate this kind of limit. So always remember that when you have a limit of some number right here, of some real number like this, whenever you have a limit that is approaches to some real number and this kind of function, it is easy when you directly substitute the value of x right here. So let's do that. Let's erase this portion of solution. This one. So let's use that solution in item number 1. So the limit of a function of x cubed plus 7x minus 10 as x approaches to 2. So when we directly substitute all that up, so we are going to have 2 cubed and then plus 7x, or the value of the x is 2, and then minus 10. So we are going to have 8 plus 14 minus 10, which is basically equal to what we have right here. This would equal to 12. So that would be the alternate solution for item number 1. Let's go to item number 2. So we have the limit of a function x minus 10 multiplied by the square root of 3x plus 7 as x approaches to 3. So direct substitution, that would be x is 3 minus 10, and then square root of 3, x is 3 plus 10, plus 7. This is 7, and this is addition. So this is basically equal to what we have in before. That would be the square root of 3 times 3 is 9 plus 7, that is 16. So we have, so this would be negative 7, and then the square root of 16 is just 4. Therefore negative 7 multiplied by 4 is just equal to negative 28. So this is basically equal to our answer using this this way of solution. So let's go to example number 3 using the direct substitution. Let's erase this one. So direct substitution for item number 3, we have 5. Our x is also 5 right here, and then plus 7, then square all that up to the power of 2. So we have 5 times 5, that is 25, plus 7 squared, this is 27, plus 7 is 32, and then squared. 32 squared is equal to 1024, which is basically equal to what we have right now. So that is guys, thank you for watching and study well. I hope you learned something from this video, and God bless.